Okay, so we learned about complex numbers right after we learn about solving equations, because sometimes when you solve equations, you get complex solutions, meaning you get solutions which are not necessarily real, which means imaginary solutions. Because remember, real numbers are complex numbers. Right? Complex numbers, the big set, it's all the real numbers plus all the imaginary numbers. So now that we know what the imaginary numbers are, we can solve some equations and not just limit ourselves to quadratics, although that is most of what we're going to do today. It's not everything we do today. I'm going to turn on there so you see a little bit before it gets too stuffy here. So the first thing, and if you read all of this, you might be confused by the words there, but I wouldn't necessarily recommend you copy that down. But the fundamental theorem of algebra, which sounds like a pretty big deal, and actually it is a pretty big deal, essentially tells you that whatever's the degree of the polynomial, that's how many solutions there are. So if you have a quadratic, meaning the degree is 2, the highest power is 2, you have 2 solutions. If you have a cubic, degree is 3, you have 3 solutions or zeros. If you have a polynomial that has a degree of n, right, which then is any natural counting number, then it has exactly that many zeros. That's essentially what this is saying. It's not exactly what it's saying, but it's what we get out of it. Right? The fundamental theorem of algebra. Again, if you're going to write anything down, I would write down this right here. Now, those zeros are in what they say complex number system, right? And we know what that means now. Complex means they might be real numbers, meaning they show up on the graph, or they may be imaginary numbers. But the total will be whatever is the degree. Done? Katerina, you done? You done? Okay. Dwayne? Okay. Let me know. So, for example, in these two problems, and today, almost everything that I'm going to show you up here, I've done an even number problem right next to the odd number problem you're going to do. Same directions, right? So if you need help, watch the video. It's exactly like we're about to do now. Right? So based on the fundamental theorem of algebra, if I'm trying to solve this equation, right, for the number 6, what is the degree? The degree is 6. So how many solutions are there? 6, right? So this is degree is 6. That's the degree. So we have 6 solutions. Okay. It's a little, you know, if you read that last slide, they didn't say solutions, did they? They said zeros. There's a little bit of a difference they're showing us here between when would you say it's a solution and when would you say that it's a zero? Zeros are for functions. If you look at their definition here, if f of x meaning it's a function, right? That's something that has a complete graph, and we're looking for the x-intercepts or the zeros to be the solution, right? Here it's not a function. It's just an equation. There's no y equals, so it really doesn't have a graph. That's why they're using the word solutions. Sometimes they're going to use the word roots, right? Not zeros, but it's all the same thing. Okay, how about the next one? What's the degree? Yeah, the degree is 5. That's degree. So how many solutions or roots are there? 5. Right. Okay. Okay, Ariel? Good? Yeah. And look. Okay, so complex zeros can be real or imaginary. The real zeros will show up as x-intercepts on a graph. Right? I mean, they could either show up like a graph looks like it's going right through the x-axis, something like this. Two x-intercepts, two answers, two complex solutions. Or they could show up like this. Right? Something like this is showing you 3 solutions. This is 1, that's 2. Because when it comes down and just touches the x-axis and goes the other way, that means there's 2. It's occurring twice. Now, the imaginary zeros, if, for example, it looked like this, right? This is a cubic, right? This is f of x equals x to the 3rd plus 1, which means how many solutions should there be? How many zeros should there be? 3. And you see one of them right here, right? The other 2 are imaginary, and you have to solve for those, right? Because they don't show up on the graph. So that's what this is talking about here. I mean, what was the other? The other one we show all the time is, you know, a quadratic. A quadratic which opens up but is above the middle, so it never crosses the x-axis. It still has 2 zeros. They're just not real. That's why they don't show up as crossings of the x-axis. So here's a couple equations. And again, these are the directions for 2 odd number problems which are right next to it. Again, how did we say we can realize how many real solutions there are? They would show up as x-intercepts on the graph, so you could just look at the graph. Let's say I'm going to put this first one in, and let's see how many zeros we see. So here's the calculator. So 1/3 x squared, I'm going to use my fraction 1 square 3. Then I go over to x squared minus 5x plus 25. Enter. And then look at the graph. It's a parabola. We don't see the whole parabola, but we can see enough, can't we? It's coming down here and going back up again. How many real zeros does it have? That's none, right? Because how many would we expect? Because it's second degree, we would expect 2, right? But this quadratic never touches the x-axis, so it has none, right? It would show up as an x-intercept, and it doesn't. So you have to say from the graph, I can. Right, that's this one right here. No real solutions. Now, is there any other way we could figure that out? You could use quadratic formula and just see. And if you solve and you get real numbers, then that's it. So let's try this one. This one I'll use the quadratic formula. So this will be x equals negative 1 plus or minus the square root of negative 1 squared minus 4 times 2 times negative 1. All over 2 times 2. Now, what part of that quadratic formula is telling us whether we have real or imaginary solutions? If there's imaginary solutions, where are they going to come from? The square root of negative 1, right? That's where they would come from. So everything depends on what's the value of that, okay? And that part of the quadratic formula actually has a name. It's called the discriminant. Right? B squared equals discriminant. If that number is less than 0, then you're taking the square root of the negative and you don't have any real solutions. If that number is greater than 0, then you're going to have 2 real solutions. If that number equals 0, that means you're plus or minusing a 0, so you're going to get the same solution twice, just one solution. So what is this? Negative 1 squared minus 4 times 2 times negative 1. That's 1 plus 8, which is 9. So we're taking the square root of 9. This will be 1 plus or minus the square root of 9, which is 3 over 4. Now, they didn't ask us for the solutions. They just said how many real solutions. How many real solutions will we get? 2. We'll get 1 for the plus and 1 for the minus. Okay. Again, how would it have been only 1 real solution? If we were adding and subtracting a 0, because the discriminant was 0, then it would have been just 1. But it was, so this one is 2 real solutions. Right? If we could have graphed it, if we graphed it, it would have shown up as the 2 x-intercepts. That probably would have taken you less time. We good? Okay, then the next group of problems are, it just says solve, okay? And by implication, they could be real, they could be imaginary, they're all quadratic. These next 3 are all quadratic. So we're gonna solve any way we can. This one here, is it necessary to use quadratic formula for that? I mean, this is one, because there's no linear term, you could just solve for x squared and then take the square root of both sides. Right? Let me add 1. Now we have 3x squared equals 1. Divide by 3. So we've isolated the x's all in one term because there is only one x term. And now if we take the square root of both sides, we'll have our answers. So x equals, take the square root, x equals plus or minus the square root of 1/3, which is 1 plus or minus 1 over the square root of 3, which is plus or minus root 3 over 3. Remember, just like we don't like to have our imaginary numbers in the denominator, we also don't want to have square roots in the denominator. So we rationalize the denominator by multiplying by the square root of 3 over the square root of 3, and you get root 3 over 3. You get to trigonometry to do that all the time. I think this one, when we went over it in P.2, was called extracting square roots. Okay. And of course, it's a special case. It's a special case where you don't have the linear term. Now, could you use quadratic formula on that? Sure. If you wrote this like 3x squared plus 0x, because there's no x term, minus 1, then you would have a is 3, b is 0, c is negative 1, and it'll work. You'll get the same answer. Okay, another solve a quadratic which looks kind of different. And it's actually kind of the same as the last, which is right now we only have one x term, and it's inside parentheses being squared. So the strategy will be, let's solve for the squared term, and then we'll take the square root of both sides. Now, any other way you could do it? You could FOIL it, right? You could FOIL the x minus 1 times x minus 1, simplify, combine like terms, and then use quadratic formula or factoring or whatever comes up. But I think what they would expect, and you've got a problem again right next to it, which is written almost exactly the same way. They would expect that you're doing this. Add x minus 1 squared to both sides. And then you're going to get x minus 1 squared equals 16. Right? Once you've solved for the squared term, meaning it's isolated, there's nothing else with it on that side, take the square root of both sides. The square root, the square root. What do you get when you take the square root of a square? What's the square root of x minus 1 squared? X minus 1, right? The square root cancels the square. And what do you get when you take the square root of 16? Plus or minus 4. Right? It's not just 4. When you take the square root, you've got to take into account the plus and the minus. So plus or minus 4. Okay, you still haven't solved for x. Add 1. So x equals 1 plus or minus 4. X equals 5 and negative 3. Right? Add it the first time, subtract the second time. Okay, Mackenzie. Okay, see. Okay. Here's another one. Okay, this one has the linear term. This one has the linear term. So you're going to have to solve it by some other means, right? You're not going to be able to solve it by extracting square roots because there's no way to isolate the variable in just one term. So you could factor it. If you could say 4 times 1 is 4, can you think of factors of 4 that add up to 4? How about 2 and 2? So this is factorable. What else could you do? What's another method to solve this? If you don't want to factor, if you don't want to remember all those 6 steps that it takes to do it. Say again? I mean, you can always use quadratic formula. What's another way? You could graph it, right? And what would you look for on the graph? The x-intercepts. So let's do it that way. Let's do it by putting in the calculator, looking for the x-intercepts. Y equals, clear, 4x squared plus 4x plus 1. Okay, and I look at the graph. A normal graph would look like that. Okay, now I'm going to zoom in because I can't hardly see what's going on there, so I'm going to zoom in. So zoom, and 2 for zoom in, and you can see it right there. Okay, now, what is the value of that? You could try to estimate, but something you should know how to do with your calculator is let the calculator find the zeros. And some of you may have done this already. If you haven't, I'm just going to step through it once, and you may probably need some more reminding of how to do it in the future, but we might as well start doing it. If you look above the trace key, it says calc. If you go second trace key, number 2 is 0. Okay, so I say 2. Okay, it's going to ask you 3 questions. The first question is left bound. What it means is put in an x value which you can tell is to the left of or less than the 0. Well, that 0 right there is in between 0 on the right and -1 on the left. So you could put in any value which is to the left of that as long as it's on the screen. Okay, and you could do it 2 ways. You could just enter it in. I can say -1, enter. That would be good. Or you could use the cursor and just move the cursor over to the left. All right, watch this. When I get it so it's clearly less than to the left, then I hit enter. And then it's going to ask me for the right bound. Right? For the right bound, I can either, again, arrow over so the cursor is somewhere to the right, or you always have the option to just enter an x value that you can see is to the right. For example, if I say 0, enter. That's good. So you have 2 options. You don't have to move the cursor. Sometimes I think it's even harder to use the cursor. And then it's going to ask you to guess, meaning it put 2 little triangles on the graph. This was the left bound, that's the right bound. If you're happy with what you did there, then, and you always are, right, then you just say enter. When it says guess, say yes. And then it'll go right to the 0, which looks like it's 0.5. It's 1/2, -1/2. Sorry, there's a negative in front of that. So let's capture that to put in the slides. Get rid of that. Okay. So let's see. Solve. X equals -0.5 or -1/2. So it's just 1. Now, again, what do you know by the fact that it actually shows up as a touching of the x-axis, and then it goes back up in the same direction, that means it's there twice. Right? That means if I was going to break, this is actually 2x plus 1 times 2x plus 1. Negative 0.5 is the 0 that comes out of both of those, so it's there twice. Which means when you touch it, let's say it's positive, right? And then it's equal to 0, and then when you got on the other side, it's still positive because you're squaring something. Something squared is always positive. It doesn't change sign. That's a sign of the 0's there twice. Okay. And then one more time. This is one, we'll use quadratic formula just to show a bunch of different ways of doing this. So x equals negative 4 squared plus or minus the square root of negative, what am I doing here? Getting ahead of myself. Negative 4 plus or minus the square root of negative 4 squared minus 4 times 21. Two times 4. Okay, x equals 4 plus or minus the square root of 16, and 4 times 21, that's 84 times 4, which is 324, divided by 8. So x equals 4 plus or minus the square root of 24, that should be negative 308, divided by 8. So what kind of solutions are we going to get? They're going to be imaginary. Because of the negative in there, they're going to be imaginary. And I would bet that we can simplify the square root of 308. Let me think. Is it divisible by a square, a perfect square? At the very least, it looks like it's divisible by 4. Because you can always tell if the last two numbers are divisible by 4, then the whole thing is divisible by 4. So let's try this. 308 would be 4 times 78, 77, 4 times 77. Okay, that's good. And then would we be able to split, to simplify the square root of 77 any further? 7 times 11, they're both prime numbers. So, you know, the square root of 4 times the square root of 77 is 2 times the square root of 77. So this is x equals 4 plus or minus 2i times the square root of 77 over 8. And because 2 divides evenly, do you get it? What do you mean here? The square root of 4 is 2, right? So I'm saying the square root of 308, which is our problem over here, I can break up the 308 into 4 times 77, and then take the square root of 4 times the square root of 77, 2 root 77. Okay, now here we've got 4 and 2 and 8, and they're all divisible by 2. So I should write this as 2 plus or minus I times the square root of 77 over 4. So would it have worked for us to try to find these answers on the graph? It's imaginary. They wouldn't show up on the graph. You had to use quadratic formula. That's why quadratic formula is the one that always works. Right? It always works. You're going to get an answer out of it. And a solve. So now this is, what do you notice about this one? It's not a quadratic. And there's not a lot. I don't recall that they even did this when we were doing the section on just solving equations. And it used to be in the prerequisite section of the book, there was a particular part that addressed just this kind of equation, which was called the quadratic type. It's not a quadratic, but it'll factor just like a quadratic. Right? This is quadratic type. Meaning, if we were factoring a quadratic that looked like this, we would say to ourselves, what two numbers, the product is -8 and the sum is 2. And what two numbers would we come up with? Product is -8 and the sum is 2. +4, -2, right? So +4, -2. But we don't have a quadratic. So the first term is not x, it's x squared, right? X squared. So factor it just like you factor a quadratic. But instead of having x as the first term, you have x squared. And if you're not comfortable with it, FOIL this and see that you don't get back to exactly this. X squared times x squared is x to the 4th. X squared times -2 is -2x squared. X squared times 4 is 4x squared. 4x squared minus 2x squared is 2x squared. 4 times -2 is -8. Okay, once we get to this point, use zero product property, right? If we're making a zero through multiplication, it must be the case that either this factor equals 0 or this factor equals 0. Right, solve. Right, this one, x squared equals -4. X equals plus or minus the square root of -4, which is plus or minus 2i. And then solve this one. X squared equals 2. X equals plus or minus the square root of 2. Right. How many solutions did we expect? It was a 4th degree polynomial, so we should get 4, right? And here's 1, 2, 3, 4. How many of those would have shown up if we looked at a graph? These two would have. These two would not, because they got I in them. Okay. So imaginary zeros are found by solving quadratic equations, right? In the end, every time we get down to the i's, it's because we took the square root in the process of solving a quadratic. I mean, it could have been a higher degree polynomial to start, but we had to solve a quadratic in the end, and that's where the i's came from. The thing is that those solutions, because they come from taking square roots or quadratic formula, they're always going to occur in pairs. They're always going to be conjugate pairs. We know what that word means now, right? If you have 1 plus 2i as one of your zeros, you've got to have 1 minus 2i because it came from a plus or minus situation, right? If you have -4i, you got to have positive 4i, right? The imaginary solutions occur in conjugate pairs, right? Generally speaking, if one of them is a plus bi, the other is a minus bi. Good? Not yet? Okay. So this, again, you probably have number 53, and this is 54. So you're going to want to do exactly what we're doing here. You're asked to find all the zeros if they've given you one imaginary zero. Okay, well, let's see. What's the degree of the function that we're trying to find the zeros for? Is 3, right? So we expect 3 zeros. We've been given 1 is 3i, so tell me another one. Negative 3i, right? See, 2 out of the 3 you already know because you got to have the conjugate pair. So you got to have negative 3i, right? There's a 0 because it's a conjugate. Okay, so there's going to be one more. Could the other one be an imaginary 0? Could the one that's left be an imaginary? Why couldn't it be imaginary? Because you'd need a conjugate, and then there would be 4, but there's only 3, right? So what do you know about that last one? It's a real number. So how can you find the last one? Look at the graph, right? So let's look at the graph. Yeah. I'll put it here. No, I can't do that. If you're writing there, I don't think that's going to work, but let's do this. X to the third, X hat 3. Make sure you get out of the exponent, plus X squared, plus 9X, plus 9. Zoom 6. Do you see any zeros? Negative 1, right? It looks like negative 1. How can you confirm? Well, you could do the second calc 2, right? You could do that. Or you could look at the table of values. Usually your table of values, which is above the graph, is set to tell you for all the integers, values of x, what the values of y are. And you can confirm it right there. So you don't have to do anything else. It's right there, right? This could have been more complicated if it was in between those numbers, but then you do the second trace to left-bound, right-bound guess. Okay, and just to be clear, let's say I'm going to the graph here. It is not accurate enough to just hit trace and then let the trace get as close as you can get it, right? That is not going to be accurate enough. You have to do the second calc to left-bound, right-bound guess if you're going to do that route. Don't just use the trace because it will not get right on the x-axis. So from the graph, and I'm not going to cut this out, from the graph, it looks like our last 0 is negative 1. Okay, then the last, this linear factorization theorem. Again, you don't want to copy all this. We don't have time for all that. It's going to cut into your quiz time. But basically it means this. If you have a 0 of x equals 1, that means you've got a factor of x minus 1. Whatever's the 0, x minus the 0 is called a linear factor. If you have 3 zeros, 1, 2, and 3, then you have 3 linear factors, x minus 1, x minus 2, x minus 3. Right, that's what the linear factorization is. What makes it linear? What does it mean for linear? X is to the first power. And every one of these is x to the first minus the 0. Linear factors. So the last 2 problems are like this. It says, find a polynomial if you're given some zeros. Okay, well, let's see. The 2 zeros I've been given here, 4 minus 3i. Or sorry, 4 and negative 3i. But you know one more 0, don't you? There's one more 0 that has to be there, even though it's not written. And what is that? Positive 3i, right? It has to be in conjugate pairs, so you know you've got that. Okay, well, if those are the zeros, what are the linear factors? Again, how do you make a linear factor out of a zero? X minus, right? So we would have x minus 4, x minus negative 3i, which is x plus 3i, and x minus 3i. Okay, now when asked for the polynomial, that's the polynomial in factored form. You got to put it into the standard form, meaning you have to multiply, right? And usually, if you got the complex conjugates there, then what you want to do is multiply those, right? Don't choose to do x minus 4 times x plus 3i. You're going to make it more complicated than it needs to be. Right? First, do these, because they have your complex conjugates. Right? If I multiply those, I'm going to get x squared minus 3ix plus 3ix. And then the plus 3 times the minus 3 is negative 9. But there's also an I squared in it. And I squared is negative 1. So negative 9 times negative 1 plus 9. Okay, we can simplify that. These cancel. So you've got x squared plus 9 times x minus 4. Now you have to multiply one more time. FOIL it. X to the third minus 4x squared plus 9x minus 36. What's that? That's the answer. When it says find a polynomial, that's the polynomial, okay? In standard form, not just with the i's in there, or the parentheses in that. And it could get one more step more complicated. If that imaginary zero has actually got a real part and an imaginary part, this is what it'll look like. And I'm just going to go through this quickly, and it'll all be in the video and the notes and everything on the web page. But what's the other zero? 3 plus 2i, right? 3 plus 2i. So what are our linear factors? X minus 5 comes from there. X minus 3 minus 2i is from there. And x minus 3 plus 2i is from there. And I would simplify those, distribute the minus. Right? And remember, the thing that's changed here, this minus turns is to a plus. Don't change the x minus, which is making it a linear factor. Right, so this is x minus 5 times x minus 3 plus 2i times x minus 3 minus 2i. Right? Now, again, it's going to be a two-step process. First, you're going to have to multiply the linear factors that have the imaginary number in it. And then when you're done with that, multiply by the other. Do you have a question? I can't hear you. Here? Here? This is how you make a linear factor. You take x minus the 0, just like we did here. How did this become an x minus 5? We put an x minus in front of the 0. That's all I did from here to here, from here to here. It's exactly what we did in the last one. Right? We went from 4 to x minus 4. X minus negative 3i is that. X minus 3i is that. And whenever I get like 3 terms times 3 terms, the way that I would do that is I would try to, because that's not a FOIL situation. There's too many things going on there. I would use this method. You can end up doing it your own way, but you got to get it right. And that is this. Make yourself a grid. And along one side of it, put x minus 3 plus 2i. X minus 3 plus 2i. Along the top of it, put the x minus 3 minus 2i. And then fill in the grid by multiplying what's at the left and what's above. So this first one will be x times x is x squared. X times negative 3 is negative 3x. X times negative 2i is negative 2ix. Okay, next row, negative 3x. Negative 3 times negative 3 is 9. Negative 3 times negative 2i would be positive 6i. Right? 2i times x is 2ix. 2i times negative 3 is negative 6i. And 2i times negative 2i is minus 4i squared. But that equals plus 4. Right? Now, look and see what happens when you combine like terms. You have a plus 2ix and a minus 2ix, so they cancel. And they always will, okay? You have a minus 6i and a plus 6i, so they cancel. And they always will. Okay? And all that's left is x squared. Negative 3x minus 3x is minus 6x. And 9 plus 4 is 13. Okay. And then I'm not going to take this last step, but then you just do it one more time. You're going to have to multiply this times this. And I would recommend do it like that. Put the x minus 5 here, put the x squared minus 6x plus 13 there. Okay, that is the end. We need to get started on a quiz. Need to take out paper and something to write with. I'll write the homework up on the board while you're taking the quiz. Make part 2. Okay, so we finished that one? Is anybody still copying on it? Yeah. Well, if the only reason we did it here is because then we're something we could cancel. You wouldn't be able to do that if it was just straight, one a plus bi complex number. There would be nothing to cancel. It's only because we have a numerator and denominator it actually simplifies. So, yeah, I would not. If it says 2 plus 4i and that's your whole answer, then that's your whole answer. We good? Yeah. So, but we did all of that so that we can actually solve a problem like this with the quadratic formula. And so I'm going to use the quadratic formula. X equals, do it here. X equals negative 14 plus or minus the square root of 14 squared minus 4 times 8 times 9. Okay, do not eat in here. Do you understand? 2 times 8. Okay, we get negative 14 plus or minus the square root. And what's 14 squared is 196. 4 times 72 is 288. 196, 92. the square root of negative 92 over 16. Now, see, could we simplify that at all? Well, here's one thing we could do. How do we simplify the fact that we've got the negative inside the square root? We take out as an I, right? So now we're going to say x equals negative 14 plus or minus, and there's going to be an I that's outside of the radical. But what about the square root of 92? The square root of 92 is 4 times 23, which is 2 times the square root of 23. Right? 92 is 4 times 23. 4 simplifies. So we have 2I, the square root of 23, divided by 16. Now, we can simplify it one more step like we did on that last problem, right? Because all of the numbers that are not inside the radical are divisible by 2, right? But something to notice is because of where these solutions come from, the I solutions, they come from the quadratic formula. They always have a plus or minus in the middle, right? And the only difference between complex conjugates is the sign in the middle. Well, that means that you're never just going to get one complex number as a solution. You're always going to get 2. You're always going to get a complex number and its complex conjugate. They have to occur in pairs because of that, because that's where the I comes from, the plus or minus. So again, if I took this one more step, if I factored out a 2 as a numerator and denominator, it would be negative 7 plus or minus I times the square root of 23 divided by 8. Right? So complex conjugates always occur in pairs as solutions to quadratics. They always occur in pairs. You okay? Tutto bene? All right, that's what we did. Like I said, most of it should be a review. We did it more or less the same way in Algebra 2. Right, these are the homework problems, and the quiz next class is on P1 and P2. Just a second.